In our last video, we looked at a t-test, specifically a one-sample left-tailed t-test, and kind of went through all the steps of performing that hypothesis test in some detail. In this video, we're going to be looking at using TI calculators, the apps that are built in these for performing t-tests to help us short-circuit this or to give us a little shortcut. So, just as we have seen z-interval, z-test, and t-interval apps built into the TI-84 and TI-nspire calculators, we similarly have a t-test app built into these calculators as well. And we'll illustrate this to begin with the problem from the previous video. And if you look at it, this is the same value, same problem that we had in the last video. So let me refresh your memory if you don't remember from the last video, or if you haven't watched the last video. We're looking at a problem where the recommended amount of sleep for adult humans is 8 hours per night. However, a student life publication of university indicates that an average amount of sleep of college students living on its campus is actually 7 hours per night. A random sample of college students were surveyed to see how many hours of sleep that they got per night, and the data was displayed below. We want to test the hypothesis that the students actually get less than the reported 7 hours of sleep per night, and we're going to use alpha equals 0.1, which is called our significance level, and then there's the data and number of hours per sleep per night. Well, after having done a few of these tests on your calculator, I think you'll probably find this pretty straightforward. First of all, we need to get our data in. So if you still got this data in from the last video, then there it is. If not, we can go in and fix that. We put our cursor, we go to Stat Edit on a TI-84, go put the cursor on the L1, hit Clear and Enter. Then that'll clear out the list. Type your data in one at a time, hit Enter after each one. That gets our data in list 1. Then go back to the home screen by doing Quit, which is second mode is Quit. And then you go to Test, so that's Stat, and then left arrow to Test. Choose number 2, which is the t-test, and that gets you this screen here. We can either enter in our summary statistics, or we can enter it in by entering data in. We have our data entered in, so we're going to click Data. The null hypothesis is that the mean is 7. The data is in L1, frequency 1. Our alternative hypothesis is that mu is less than mu naught. And I can either click on Calculate or Draw. If I click on Calculate, it gives me this screen right here. And it tells me the alternative hypothesis, mu is less than 7. Okay. And it tells me the t-value is negative 1.586, etc., the t-star test statistic. It tells me my p-value, probability p-value, the probability of getting a test statistic this extreme or more extreme, and then the standard deviation of the sample, and then the sample size. So it kind of summarizes that. If you hit Draw instead, it draws the t-distribution with n-1, that's 9 degrees of freedom. And the area that it shades is not alpha, but p. Notice we never actually put in alpha. So it's actually the p-value there. And so we see that drawing if that's what we want. If we hit the draw button. It does still return the test statistic t, maybe a few fewer digits of it, and the p-value there. You can get more digits of that either by going back and doing this again and look at this screen, but it actually saves these t and p under variables, VARS, and in statistics if you want to go back and find those. Notice that the only thing it really doesn't do is the critical value, and of course we can do the critical value by doing an inverse t. Well, in this case, the critical value is a boundary of an area like this, not this one. It's actually a little bit bigger one, an alpha of area of alpha, but it's to the left, and that area to the left, or probability to the left, is 0.1, and the degrees of freedom is 9. So you just plug that in as an inverse t, and you have to calculate that separately if you need it. But actually you don't really need it because you can do the test completely in terms of the p-value. So the calculator basically uses a p-value approach. This slide here basically shows the same thing done on a TI-nspire calculator. So let's start back at the beginning. Make sure that you have a spreadsheet page. Go to menu and add, or home and add one if you need to. Then I gave it some descriptive name like sleep in this case, and then typed in my data. First make sure that that column is cleared out, and then you can type in that data. Then go back to a calculator screen. Okay, and again, add one if you need to. And here we hit menu, and we choose statistics, which is number 6. It's kind of buried back here in this list here. And then stat test is the last one down here. I believe that's 7. And then t-test is number 2. So that's menu 672. And then this screen comes up here, and you have a choice of inputting either data or statistics. Choose data in this case. Click OK. You have to put in your null hypothesis, which was 7. The list where our data is, which we called sleep. And you just click on this arrow here, and some choices will pop up, and sleep is there. Frequency list is 1. The alternative hypothesis, it shows there, in our case, is that mu is less than mu naught being the 7. Once you get all that, those 4 things figured out, click OK, and then it returns this particular little table here. And so notice that we see the alternative hypothesis is listed, mu is less than mu naught. The test statistic is negative 1.58 whatever. P-value is 0.07 something. It also returns the degrees of freedom, the x bar, the s of the x's, and for our sample, and then the n value, basically the same thing returned by the TI-84. And the only thing it doesn't do is a critical value, and if you need that, you can do it separately again as an inverse t of 0.1, 9, and there's a critical value if you need it or if you decide you want it. Okay, so that's the nspire version. So this slide is exactly the same as the one from the last video. Once you have this data in hand, then you can make your decision. So the critical value method, if we went ahead and did that extra work of finding out the critical value, then we can compare the test statistic of negative 1.59 to the critical value of negative 1.38. We notice that T star is less than C, and this is a left-tailed test, so that puts the T star in the critical region. And so we would reject the null hypothesis in favor of the alternative hypothesis. The p-value method is probably the way you're going to want to do these because it's kind of the native way the calculator does it, and because some other things too. When you report it, if you just report this p-value, someone else can look back and decide if it's a good way to do this, if they would make the same decision based on that p-value or not. So if they have a different sort of level of alpha, a different threshold for a type 1 error, then they can choose to make that decision without doing any further computations. And that p-value gives you some idea of the strength and how confident you are about your conclusion. But for the alpha value chosen, we notice p is less than alpha, and so that's always a reject the null hypothesis in favor of the alternative hypothesis. And some of the numbers are rewritten down there at the bottom. So then we write our conclusion. The mean amount of sleep for the students in the sample was 6.5 hours per night. This results in a p-value of 0.0735 from our one-sampled left-tailed t-test. So at the alpha equals 0.1 level of significance, we see that there is sufficient evidence to conclude that the average amount of sleep for all students at this university is less than the hypothesized 7 hours of sleep per night. Notice in our conclusion we include the sample mean, hypothesized mean, p-value, alpha value, type of test, and our conclusion stated in the context of the problem. Now we just rejected the null hypothesis. So could we have made a mistake or could we have gotten it right? Well, it could be either one. We don't really know. I mean, the truth is either the average amount of sleep is truly is 7 or it's not. Or it's less. It might be less. But the question we don't really know that. And the only way to find out, of course, would be to actually test everybody in the university, which we can't do. So we could have either made a type 2 error or type A correct conclusion. or we could not have made a type 2 error or type A correct conclusion. Those are impossible for us. So the probability we did one of those two things is 0, because both of those require us to not reject the null hypothesis. So a type 1 error, which we hope we didn't make, would happen if in fact the null hypothesis that the mean amount of sleep in university students is actually, that should see 7 hours per night, and we incorrectly rejected it. Now remember, the alpha level gives us our level that we're willing to accept, so we were okay with having this happen with probability 10%. If we only rejected samples with a test statistic at or more extreme than the one we got, then we would make a type 1 error only with probability of 0.0735, or just a little over 7%. So certainly that's under our threshold of alpha, and so we're okay with this. But there still is some probability, small probability, that we did make a type 1 error. However, what we really hope is that we made a type B correct conclusion. This would be that we are correct in our conclusion that the mean amount of sleep by these students is less than 7 hours per night, and we are 1 minus P, that is about 93, about almost 94% confident that we have made a correct conclusion. Okay. So let's let you do an exercise this time, and we can use the full power of your calculator here. A machine fills cups with coffee. A sample of 20 is taken, and we find that the average amount filled in the sample is 8.05 fluid ounces, and the sample standard deviation of the sample is 0.1 fluid ounces. A dot plot of the data suggests that the individuals are distributed fairly close to a normal distribution. Or perhaps we did a normal probability plot and found that was true. So the machine is supposed to distribute 8 fluid ounces of coffee. Assume that this really is the mean of the distribution of the population. What is the probability that the average of a sample of 20 cups from a hypothesized population is more than 8.05 fluid ounces? That it's 8.5 or more. Okay. And what would this be? See if you can press pause and figure this out now. Okay, now that you're back, let's take a look at this. So here I've computed and done this with shading. So what we're doing is we're finding a probability from a t distribution, right? Where there is the probability that it's more than 8.05 ounces. Now I don't know if I've shown you this one before or not, but you can go to second VARS for distributions. This is on a TI-84. Instead of going to distribution, go to draw, and there's certain ones here, the most important ones that we do for inferential statistics, normal, t, chi-square, and f, we can draw and shade. So we can select shade t, and what we have to do is we have to put in our test statistics. So here's what our t statistic. So I put in 8.05 minus 8 in parentheses divided by parentheses 0.1 divided by square root of 20. That's x bar minus mu over s divided by square root of n. So I might have just probably been better off if I just figured that out and stored it as t first, as is t star, and then shade t from that t up to, well, I went up to 50. That was plenty big enough. And with 19 as the degrees of freedom, that's one less than the sample size. And we see this here, and it's shaded. It's hard to see here because it's just a little bitty bit here shaded on the right side, which you can't really see. And it also, though, it tells you its area is 0.01877, and we went from 2.23607, so that's our t star value you got by doing 8.05 minus 8 divided by 0.1 divided by square root of 20. and the upper I went to 50. Technically it should be going to 100. 50 is going to work okay, and the degrees of freedom are 19, so that's what we get there. We could have gotten the same number by doing this from the home screen as well. Now, what's a 90% confidence interval for the true mean of coffee dispensed? So this is actually a T interval. See if you can go ahead and work this one on your own. Press pause now. Okay, well, we've done this before, and we go to, on the TI-84 at least here, we can go to Stat, go to Test, go down to number 8, which is a T interval. This is from statistics. We put in the X bar is 8.05. The S of X is 0.1, N is 20, confidence level is, that should say 0.90, and then calculate, and then here's our T interval right here, and it tells us X bar, S, and N as well. So there's our T interval. So we're 90% confident that the true mean of coffee is somewhere between, let's say, about 8.01 and 8.09. Now, let's do an actual hypothesis test now that the mean is actually greater than 8 fluid ounces that is advertised. Okay? So we want to figure the critical value associated with this. For alpha is 0.05, 5%, and the test statistic. Let's see if we can figure that out first, okay? Press pause if you and get this and come back. Okay, so the inverse T of 0.95, 19 is the test statistic, the critical value. The test statistic, we just talked about that, is 8.05 minus 8 divided by 0.1 divided by square root of 20. Notice the parentheses there. So that's X bar minus mu divided by S over square root of N. And that's our test statistic, T. And the inverse T of 0.95. Now, why 0.95? Now, this is a right-tailed test. The alternative hypothesis is that mu is greater than 8, and mu equals 8 is the null hypothesis. So since this is a greater than 8, we want the 0.05, actually, 5%, to be the probability to the right. But the inverse T is you always do the probability to the left. So here we're going to put in, instead of putting 0.05 here, we do 1 minus 0.05, or in other words, 0.95, to do the inverse T to get the critical value. Now let's actually do a t-test. We could actually do this, we almost got all the stuff worked out for it already individually, but we can also just have the calculator do it for us. So again, we go to Stat, left arrow to Test, choose number 2, t-test. We're going to input our data from statistics, so make sure that's on stats. Mu naught is 8, our X bar is 8.05, S sub X is 0.1, N is 20, and this is a right-tailed test, so the alternative hypothesis is mu is greater than mu naught. If I hit calculate, I get this screen. If I hit draw, I get this screen. Both screens give me the T value, the T star value, and the P value. We'd already computed that T star already. The P value there is the P value of the test. Okay. And then it summarizes X bar, S, and N as well. Now, how do we make a decision? Well, we compare the alpha value to the P value. If the P is less than alpha, then we reject the null hypothesis, and then we say we do have enough evidence that the alternative is true. If P is greater than alpha, then we fail to reject. So in this case, P is about 0.019. That's less than a 0.05, which is our alpha level, so we reject the null hypothesis. Notice had we used a different alpha level, say 0.01, then we would have failed to reject. So we have some pretty good evidence that the machine is filling these cups of coffee a little bit more than 8 fluid ounces on average. So here's our conclusion, at which we can state like this: performing a one-sample right-tailed t-test with a significance level of alpha equals 0.1 produced a p-value of 0.0188. So there is enough evidence to conclude that on average the machine distributes more than the indicated 8 fluid ounces of coffee. We're 90% confident that the true mean amount of coffee is distributed by the machine is in the interval 8.01 ounces to 8.09 ounces. And so this combines a t-test and a t-interval in our conclusion. Let me ask you a couple other questions. What's the probability that a particular individual will get less than 8 ounces of coffee, or that one that will get less than 7.9 ounces of coffee if the true mean actually is what our sample mean was, which is 8.05? Now we're sort of changing our assumption that the sample mean is really representative of the true mean. If that's the case, what are these probabilities? Go ahead and figure these out now. Press pause. Okay, you should have done these on your calculator by now. And so here, those are just probabilities from we can do this from a normal distribution. We're talking about the individuals. The individuals we're assuming are distributed normally. And we could look at this as just a normal distribution. Now I'm talking about individuals, not means now. See, this is a question about individuals. Whereas t-test and t-intervals are questions about averages, about means. So here the probability of a particular individual getting less than 8 ounces of coffee turns out to be about 30.85%, which we find as normal CDF from 0, why 0? Well, technically it should be like negative infinity, but if it's making coffee and filling a cup, you can't fill it less than 0. So in the practical sense, starting at 0 makes sense here. So 0 to 8, with 8.05 being the mean, 0.1 being the standard deviation of the individuals. That gives you 0.3085. Then we do the normal CDF of from 0 to 7.9 with a mean of 8.05 and standard deviation of 0.1, and we get 0.067 roughly, 6.68%. So the probability that they get something less than 8 ounces, if the true mean was set at 8.05 ounces, is about 31%. But the probability that they'll get less than 7.9 ounces is only about 6.7%. So they would probably, in reality, they might set the machine so that it averages slightly above 8 ounces, so that not many customers would get a noticeably less than 8 ounces when they get their coffee in. All right, so there's a good example, a couple examples in this video of how we can use the calculator technology with t-test, and we even reviewed some t-intervals and a few other things as well. So hopefully we can now use that in some more examples on the homework, and in a couple more videos we'll look at a couple more examples here coming up as well.